In section 2.6, we start talking about free-falling bodies, right? And free-falling bodies, basically, now we're talking about things, up until this point, we were talking about things in the x direction, so horizontal movement. Now we're going to start talking about things that are going in the y direction or the vertical, right? So basically this notion of free-falling bodies, it says, in the absence of air resistance, it is found that all bodies at the same location above the Earth fall vertically with the same acceleration. It is important, as I've mentioned before, that yes, it does matter how far above the Earth you're talking, and that's why they put the stipulation on here that they're at the same location above the Earth, and it has to do with gravitational pull. So the bodies that would be falling have to be the same distance above the Earth, and they will fall with the same acceleration. So this idealized motion right here, in which air resistance is neglected and the acceleration is nearly constant, is known as free fall. So we do have to neglect air resistance, though, and that's what we will, unless otherwise stated within the problem, you will always neglect air resistance, all right, because they want everything to be falling with this acceleration due to gravity, which is right here with is this g, which is 9.8 meters per second squared, or 32.2 feet per second squared. Usually, almost always, we will use the 9.8 meters per second squared, and typically that will be negative, actually, because if you think about it, things that fall always fall back to Earth, right, because of gravitational pull. So that gravitational pull is pulling it down, it's pulling it back to Earth, so down by convention is a negative in the y direction, so it's usually a negative 9.8. All right, that's acceleration due to gravity. So over here, we have this little experiment, and basically if you had a tube with a feather and a rock in it, and you flip them over, because of air resistance, that feather, that piece of paper, I think they say paper, but it doesn't matter, that paper is going to take much longer to fall than what that rock is. But if you take out all the air that's in that chamber, because there's no air resistance, both will fall at the same time. Okay, they'll both hit at the exact same time because there's no air resistance. Thus, when using the equations in Table 2.1 for free-falling motion, we will simply replace x with y. There's no significance to this change. The equations have the same algebraic form for either the horizontal or vertical direction. All that's saying is back in that Table 2.1, we had kinematic equations, and you will now replace all the places that there was x with y. So you can still use the same equations, it's just going to replace y with x, all right? So here in example 9, right, we start talking about it, and it says a stone is dropped from rest from the top of a tall building, as figure 2.13 indicates. After 3 seconds of free fall, what is the displacement y of the stone? And as I've also mentioned previously, you have to always start thinking about things that they don't tell you in the problem, but that you will know. So the thing here that they don't tell you, right, they don't specifically tell you, but it's kind of known. It says a stone is dropped from rest. Well, if something is dropped from rest, it means its initial velocity is 0, right? So in this case, they don't tell us it, but we can surmise that v sub 0 is 0. They don't tell us it, but we know by this little statement right here, dropped from rest, okay, that v sub 0 is 0. The other thing that you're always going to have to start thinking when we're talking free-falling bodies is that g is negative 9.8 meters per second squared. Most times they're not going to tell you that. But if you're talking about a free-falling body, always know the acceleration is negative 9.8 meters per second squared. All right. So at this point in time, they say after 3 seconds of free fall, what is the displacement of the stone? Well, obviously we're looking for y. We know my acceleration. We don't know v final, right? But we do know v initial. And we were told 3 seconds, so we have that. Well, okay. It says, what is the displacement? Well, if we go look at all that we have for kinematic equations, right? We go look at all of our kinematic equations, and we start looking at this formula that they have down here, which is one of the kinematic equations that we have. Well, okay, we have v sub 0, and we have t. We have a, and we have t. Well, that's a beautiful thing, because all you got to do now is plug everything in. And if my units work out correctly, which they should, when I do my cancellation of units, what better I come out with a unit for final? If I'm looking for y better be in meters. Okay. So, obviously this v sub 0 being 0 right here is going to cause this whole chunk right here to go to 0. So that zeroes out, that goes away. That's awesome. So now all you got to do is the 1/2 times the negative 9.8 times the 3, and you come up with negative 44 meters. Technically negative 44.1. Now, you're going to say to yourself, well, wait a minute, why is that negative? How can I have a negative meter? Well, if you think about this, this is y equals 0 up here, right? That's my starting location because that's where I'm dropping it from. So by convention, if it goes down this way, this is going to be in the negative direction. So that's why it's negative 44 meters. All right, so that is the first example. Now, we're going to move on down here, and they're going to ask in example 10 the velocity of the free-falling stone now. So after 3 seconds of free fall, what is the velocity v of the stone? Well, what you have to do is you have to come back up here, and you would still use all this information, okay? You now have y, you now have a, you now have v sub 0, and you now have t. The only thing that you're looking for is v. Well, what's the difference between v sub 0 and v? Well, v sub 0 is my initial velocity, where v is going to be my final velocity, right? It's going to be my final velocity. So what they're looking for is they want to know what is going to be your final velocity at 3 seconds. So if you go back and you look at your kinematic equations, right, you would look at all the ones that could work for this. And there's oftentimes more than one that you could probably use, all right? And I shouldn't say oftentimes, but sometimes there's more than one that you could use, okay? Sometimes there's multiple different equations that would work. As long as you find one, that's the important part. So in this case, they're going to use the one that is most easy to find it, which is v equals v sub 0 plus at. Well, we have all this stuff, which we know that v sub 0 was 0, a was negative 9.8, and t is going to be 3 seconds. And again, you simply plug it in and you just do the calculation. You come up with negative 29.4 meters per second. But somebody explain to me why I get a negative velocity. Because it's falling down, right. So again, just kind of like the directional sort of thing, because it's falling down, it is a negative velocity, all right, because it's going down. It's falling downward. It's a negative velocity. Good. Moving on up here. The acceleration due to gravity is always downward pointing vector. So acceleration due to gravity is always downward pointing. And again, it's because gravity is always pulling down, right? So it's always trying to pull things back to Earth. In 11, how high does it go? Okay, so now we're going to talk about a couple other things that we know. Okay. It says a football game customarily begins with a coin toss to determine who kicks off. The referee tosses the coin with an initial speed of 5 meters per second. In the absence of air resistance, how high does the coin go above its point of release? All right. I told you that this section was difficult because there's a lot of things that they won't necessarily tell you, but you have to realize that you know. So let's go look at a couple here. Suppose, right? Suppose I take something and I throw it up and it comes back down. Would you agree that that's what happens? If you take something and you throw it from here, it goes up, it comes over here, and it comes back down. Or it doesn't even have to make a big old arc. Maybe it just goes straight up and straight back down. But the point is still going to be the same. So here's all the things that you have to keep in mind. We're talking a free-falling body here. My acceleration is always what on these? Negative 9.8 meters per second squared. That's the first thing. If, say I come up here 10 feet, what's this going to have to be? 10 feet. So know that these are symmetrical. Know that they are symmetrical. So if it comes up here 10 feet, it has to come down here 10 feet. What's that? Right. But we're just saying things that go up and then come back down. Suppose it went up with 10 meters per second velocity. What's it coming down with? Negative 10 meters per second. Good. So these are all the things that you got to keep in the back of your mind, right? Hey, if it goes up here 10, it's got to come down here 10 because it's symmetrical. If it went up with 10 meters per second, it's coming down with 10 meters per second, negative 10 meters per second. If it took 3 seconds for it to get to the top, how long does it take to get back down? If it took 3 seconds to get to the top, how long does it take to get back to the bottom? 3 seconds. Again, these are a lot of the things that they're not going to tell you, but you have to keep in the back of your mind that everything is symmetrical. So if it took 3 seconds to get to the top, it's going to take 3 seconds to get back to the bottom. Now, follow me on this one because this is going to get a little tricky. Ready? Suppose I launch it right here with 10 meters per second, v sub 0, my initial velocity. So I launch this at 10 meters per second. As it goes up, what's happening to my velocity? No. If you launch it at 10 meters per second, here's one thing that you got to remember. Up here at the top, what is it going to be when it gets to the top? What's my velocity for a brief moment in time? 0. So for a brief moment in time, at the very top of that arc, your velocity goes to 0. Now, that is going to be one of the most key features that you will use in all of these problems. Because what you're going to find out is you're going to get to these problems, and you're going to have all these variables that you know, and then how many variables can you solve for at most at one time? You can only solve for how many variables at one time? 1. So what happens is you get to these problems, and you think you have a whole bunch of unknown variables. Until you stop and think about, well, my time is symmetrical. I know acceleration always, it's negative 9.8 meters per second. And if I wanted to, I can make my velocity at the top become 0. So, a lot of times you will need to use this fact, folks, that at the top of the curve or at the top of the throw or whatever, your time or your velocity becomes 0. Now, if I launched it here at 10 meters per second, what is happening to this velocity as it goes up? It is slowly decreasing. So, suppose here I'm at 9 meters per second. What am I over here? Negative 9 meters per second. Suppose here I'm at 5 meters per second. What am I over here? Negative 5 meters per second. So what you always have to keep in mind is as it's going up, it's slowly coming to zero. But then as it comes down, your velocity is once again increasing. It's going from zero, and by the time it gets back down to here, we know it has to be negative 10 meters per second. So your velocity is going to be the same, except it's going to be negative because your direction has changed. So remember those things. Acceleration, the fact that your velocity and you're at the top of the arc, your velocity goes to zero. And remember that things are symmetrical. All those things are things you want to keep in the back of your mind, all right, that will help you out on these problems. So now I come back here, and this is why I have to tell you all this. Because as we look at this, it says a football game customarily begins with a coin toss to determine who kicks off. The referee tosses the coin up with an initial speed of 5 meters per second. In the absence of air resistance, how high does the coin go above its point of release? Tell me some of the things that we know here. V sub 0 is 5 meters per second. I would agree. I'm going to switch over to red just because it's easier to see. What else do we know? You know acceleration always, which is meters per second squared. I like it. What else do I know? All right, tell me what I'm trying to find. What's my overall that I'm looking for? I'm trying to find my height, which is going to be represented as y. So that's overall what I'm looking for. So as I go look at what equations I could use, right? As I go look at my equations that I could use, now I have some choices to make. So you go back to that section 2 or you go back to that table 2.1, and you decide which one you could use to try and find your y. So we go and we look at that section 2 or that table 2.1, and we look through all of our equations, and after carefully studying it, we think to ourselves, well, none of the equations really work out perfect because I know I'm trying to solve for y, but all of them end up with too many unknown variables. So all of them have t in it, and all of them have v in it. Well, that leaves me with a problem. Because either I need a way to be able to solve for t so I can find y, or I need to be able to solve for v in order to use the equations. Now stop and think, and this is where you got to remember all those things that you know. This referee is flipping the coin. And that coin's going to go where? Okay. And it wants to know how high is it going to go? What's one of those things that they don't tell you but you do know? It does have to come down, but do we care about it coming back down? No, because all I want to know is how high is it going to go. Think about what happens at its very highest point. Oh, at its very highest point, my velocity has to become. So really, we don't care about t, and we actually do know this guy right here. So now I can come back over here and I can say, oh, hey, guess what? V is 0 meters per second. So now, if I look back at my kinematic equations, I now have enough to go ahead and solve. And that's what they're going to do. They're actually going to use, I believe, yes, this is the one that I thought that they were going to use. Actually, it's not the one I thought that they were going to use. I thought that they were going to use, let me zoom over here a little bit. So here's all the stuff that they know. Yes, this is This is the one that I thought that they were going to use. I thought that they were going to use this one here, the v squared equals v sub 0 squared plus 2ay, and we're going to have to go ahead and solve this one for y, right? So using our algebraic knowledge, we could say, all right, well, we need to solve this for y. So what you'll do is you'll say v squared minus v sub 0 equals 2ay, right? And now do what? Divide by 2a, divide by 2a, divide by 2a. And basically what you will have is, I'm going to have to move it over to, I don't know, up to here, just so I have room. Y equals v squared minus v sub 0 all over 2a. And do we have all of that stuff? Well, sure we do, because v is what? 0 minus 5 all over 2 times a negative 9.8. And what do you notice that my outcome is going to become, positive or negative? It's going to be positive, and that really only makes sense because we said that the coin was getting flipped up to the top, so y would have to be positive. And if we do out this calculation, which I'm going to erase all my stuff now, so we can actually see what the book did, but they do the same thing. Look, 0 squared minus 5 divided by 2 times negative 9.8, and they come out with 1.28 meters. Okay, and if you want to double check it on your calculator, you can, but you should also come out with 1.28. Okay, that is the part that makes this tricky, is that it's things like realizing that you're talking the top of an arc, and you can make v be 0. It's the things like knowing that time is symmetrical, okay? So then in figure 2.14, which is the coin being flipped up, now they want to know what is the total time that the coin is in the air before returning to its release point. What is the total time that is in the air before it comes back to its release point? Bless you. Think about this. Again, back to just a generic sort of thing, if it took 3 seconds to get to the top, what's my total time in the air? If it took 3 seconds to get to the top, what is my total time in the air? 6 seconds. Because if it took 3 seconds up, how long does it take down? 3. So your total time in the air would be 6 seconds. Well, since we almost have all the information right here, right? Because now we have y. Y is 1.28 meters. Why not just use this fact to find out the time to get to the top? Time equals to get to the top. And then what would we have to do to find its total time in the air? If we found out how much time it takes to get here, what would you do with that number? All right, so right here on this coin one, right? We're talking about when it gets to the top, right? Because that's what my y is. That's only to the top that we solved in this last one. It's going to get to 1.28 meters, correct? And that's at its top. So if I solve for my time in order to get to the top, but my question is asking me the total amount of time in the air, what are you going to do with this time that you just solved for? Multiply it by 2. And that's what they're going to do. That is exactly what they're going to do. So they're going to go ahead and they're going to use that information from up here, and they're going to solve for time using this equation right here. Which is the, let's see, there it is. There's the equation that they're going to use. They're using this equation right here, which we know all these things. But when we use v of 0, we're assuming that that's going to be to the top, right? So you remember that, and you got to multiply your answer by 2. So this is going to be the time to top, so time to top. And now your overall answer is 1.02, because what did you have to do with that number? You had to double it. So in a lot of cases, you got to remember if you're solving for a time and you're making it say, hey, I'm going to use this at the top because I know that I can make my V 0, that's okay. But just remember, if you're looking for your overall time, you got to double it. All right? Just keep that in mind. Free falling does not necessarily mean an object is falling down. A free falling object is an object moving either upward or downward under the influence of gravity alone. In either case, the object always experiences the same downward acceleration due to gravity, a fact that is the focus of the next example. Okay. Let's see if this is the... We're actually going to hold up there, actually, on this example. And we're going to cover the rest later in the next video because I don't want to make the video too large. So we're going to end this and call this one part 1, and then we'll do a part 2 video.